Well, that's one of the best parts about doing these things in real life. You suddenly realize that you have to navigate your whole body and not just the windows of a Zoom. So awesome. Thank you very much for joining us today. My name is Erin Chu. I'm the Life Sciences Lead on the AWS Open Data team. And today we're here to talk about advances in precision medicine for oncology. Now, I do want to frame this. I have three experts here who are data people. We are data people, and precision oncology is a field much larger than just the data used to drive insights. But just keep in mind that when we're talking about advances in the space, we are coming at it from a data lens. And sometimes we're maybe a step removed from the immediate impact in the clinic. That being said, I would love it if my panelists could please introduce themselves. We'll start with Tanya.
Hi, I'm Tanya Davidson, Acting Chief of the Data Ecosystems Branch at the National Cancer Institute's Center for Biomedical Informatics and Information Technology, or CBIT.
Hi, I'm Bob Grossman. I'm the Director of the Center for Translational Data Science at the University of Chicago.
Hi everyone, I'm Prabhu Arumugam. So I'm a pathologist and also Director of Clinical Data and Imaging at Genomics England.
And I think that we have I think roughly 4 slides for today's panel. So you're going to see our faces up here in case you forget who we are or what we do. Please refer back, or if you happen to come in a little late to the session, don't worry, we have a cheat sheet right there, larger than life. But like I said, we are kind of coming into this talk from the direction of big data in precision oncology. But we all know that precision oncology means much more than that. And I want to start off with the fact that we are all coming out of a global pandemic. And actually read in the news about a week ago that the NHS England data reports a record of 2.7 million additional cancer follow-ups. That's more than we've ever seen before in a year. It's 116% more than pre-pandemic times. And I can say, personally, my mother was one of those cases who was referred for additional cancer checks. And so when we say, how are we going to scale this sudden increased need in diagnostics and oncology, we start talking about data. But Prabhu is also, other than his current role, I know that you're also a pathologist, Prabhu. And I would love it if you could talk a little bit, when we talk about precision medicine, precision diagnostics, what are we actually talking about in practice?
Yeah, okay. So not to kind of school the educated people on the panel, but cancer fundamentally is complex. It's not just one mutation that causes everything. It's ultimately what we call heterogeneous. So you get an aggregation of multiple different kind of mutations, and then when you also add in the kind of notion of nature and nurture, smoking, that kind of evolution of cancer becomes incredibly complex. And what the traditional way was in a lab, you'd be looking at one gene, how you look at the overexpression, underexpression, what that means to kind of in that tumor, what would that be in that kind of cancer. And then you want to go from that kind of very basic in a lab, looking at a 6-well plate or a 96-well plate, what does that mean at a protein level? And then fundamentally, what does that mean for that individual? How does that impact them? And that kind of progress is actually really challenging. So my very simplistic way of kind of taking the challenges that we have for kind of clinical diagnostics is, I'd probably put it in 2 spaces. So one is the early diagnoses, and the other bit is that kind of targeted treatment. So the early diagnosis for me would be kind of, we've got lots of 30-year-olds now that are getting cancer. Why are we getting such young people who are getting cancer? So is there something in their germline that's predisposing them to get cancer? So do we really understand that? The notion of biomarkers, so can we really predict kind of blood tests that potentially, we could identify people that might be getting thyroid cancers and things like that as well. And then also from that, you'd also look at kind of population screening. So how does someone like a colorectal cancer in the UK, we will screen for what we call fecal blood. It's just basically testing your blood, your stool, and we look for small flecks of blood. And there's a real value to that kind of early precision or kind of early diagnoses. And then the other end of the scale is kind of what you probably call precision medicine. So once you've got a tumor, I think my way of putting this is everyone in this room is different. No one is the same. So actually, if you have a cancer, does that mean that every cancer is going to behave the same? Is it going to respond the same? So why does one cancer invade a blood vessel? Why does another cancer metastasize? Why does another cancer respond to chemotherapy and another one doesn't? And those are kind of really kind of difficult diagnostic questions. And so actually we've scaled a massive rate in the last few years in terms of what we have in terms of tooling for diagnosis. So next generation sequencing, high throughput scanners and high resolution CT scanners, digital pathology. And all of those kind of tools come with a lot of data. So a whole genome for us at the moment is about 250 gigabytes of data. A digital pathology image on its own is 1 or 2 gigabytes, and you've probably got 15 or 20 images. A CT scan very quickly gets a few gigabytes of data. So just to make one diagnosis, you've got so much data to get through. But actually what we've got to look at, and from a clinical point of view, is how do you take all of that data, compress it down, and say to someone kind of on the other side of the table, you have this is the type of cancer you have, this is the best treatment for you, and this is the kind of outcomes you're going to get to. And can we get to a point where we can even predict, the comorbidities you might get with chemotherapy? And I think we're at that point now where we really understand kind of cancer progression. So in England at the moment, any child that has a cancer is given a whole genome sequence as standard. And we're now really starting to see the impact of that, because actually we can make diagnoses that are really revolutionary, really change the outcomes for these children. Actually, that's what we're looking for, isn't it? Those patient journeys and those patient stories.
Yeah, and I think that's such a good point. The fact is while we are maybe a step back and we're looking at that population level, we're trying to understand the trends of cancer and how individuals are impacted.
Yeah.
Right, by those big data findings. And so we've started to see these massive data efforts, some are nationally funded, some are privately funded, and they're all getting at the same thing, which is how are we drawing insights from lots of different kinds of data. So Tanya, I'd love to ask you, I know that you manage some pretty enormous data sets that center around cancer. How have you approached, how you can integrate and aggregate and utilize in concert all these different kinds of data?
Yeah, thanks, Erin. So we have about 4 petabytes of data within our Cancer Research Data Commons, or our CRDC. Within the CRDC, we have 6 different repositories, data repositories. 5 of them are data type specific. So for example, we have a genomic data commons, a proteomic data commons, imaging data commons, clinical trial data commons, as well as an integrated canine data commons for canine cancers. Our 6th data repository is kind of a catch-all for the data sets that don't belong in any of the other data commons. So we're kind of binning the data in different types, and that allows you to really analyze the data that is the same, right? So all the genomics data together, all the proteomics data together. But it's also very important that you're able to actually analyze across all of those things. So we've replicated all the data that's available in our data repositories on the cloud. We have 2 copies of the data, one on Amazon and one on Google, and we offer 3 cloud resources that allow users to come in and analyze the data. You can search across all the data sets. You can find the data sets from the same patient, for example, might have data in the genomics data commons as well as the proteomics and the imaging data commons. You can search across all those data sets and analyze them in a workspace.
That is such a good point, though, that while it makes such good sense to have specialist repositories for specialized data. Yeah. But to some degree, we also need to bring all the data together. And the value of these data sets, like the Cancer Genome Atlas, like Genomics England, and many, many ongoing efforts, is that how do we pull together genomic, clinical, imaging, health, behavioral, wearable data? Every time I turn around, there's a new kind of data that we're like, oh, we need to capture that, right? And there are these challenges when we are suddenly trying to take all the streams and merge them into one. Bob, I think that you've probably stood up more data commons than anybody here. Can you think of any inherent challenges as you're starting to pull together all these different kinds of data?
Well, that's a good question. Thank you. I think it's helpful when thinking about that to take a step back. I think of a commons as a collection of data in a cloud, along with all the analysis tools and services and software services you need, so a particular research community can explore the data, analyze the data, make discoveries, and eventually get to have clinical impact. And if you think of it that way, there's no right and wrong way to do this, because each research community is different. So for example, the cancer genomics community needs access to very, very large amounts of genomics data at the petabyte scale, along with the corresponding clinical and imaging data, so that they could really understand the mutational landscapes and how they relate to all those things that was just described so eloquently that affect patient outcomes individually. On the other hand, proteomics and clinical data, sometimes they all come together. We do that in the Genomic Data Commons, but sometimes it's helpful, especially for things like clinical data, that they have a little more complex structure. For example, for any of you, raise your hand if you've had to work with clinical data. Raise your hand if you've been upset about how hard it is to curate that clinical data and combine it with other clinical data. So we have a problem. I call this the long tail of data curation, that for many of our problems, especially around the clinical data, it's a very, very challenging and expensive to curate the data at such a level that we could have research insights for a particular community. Mm-hmm. And so part of what I think we'll see in the landscape of data commons more generally for cancer is we'll have the general types of commons like cancer genomics, which brings together everything for cancer genomics. We'll have the cancer research data commons, which has specialized commons for different data types and allows you to bring data together for analysis in the specialized resources. But we'll also have, we see this in liquid biopsy, we see this for particular cancers, like particular types of childhood cancers. We'll have more specialized commons that are designed for a particular set of researchers, which are laser targeted on making advances. And the flexibility about the cloud is that you can have open APIs and open standards so that you can mix and match this in ways that we haven't yet done as much as they're needed.
Yeah, I agree. I think that when we talk about, how are we going to help our research community scale, it is giving them the flexibility to work with the data as they wish, but also enabling those who have that laser focus to get straight to their science and not be impeded by availability of compute or accessibility of the data. But I wanted to touch on one more thing here. When we talk about challenges of integrating data, sometimes it's not even different kinds of data, it's data at different points in time. And the value of personalized genomics, and especially in cancer, is to track an individual over the course of their treatment. And I will say, Prabhu, I have heard people literally wax poetic about the quality of the data in Genomics England. And I'm curious, as you all started to lay out your building blocks, what were things that you think contributed to the success and ongoing success of the project?
I'll be honest, I still think there's more we can do in Genomics England, but that's
fair.
Look, so the Genomics England cohort is about now 150,000, we call them participants, we don't call them patients. And we have whole genome sequences for all of them. And our consent is exceptionally broad, so we're allowed to collect longitudinal clinical data, electronic health records that we can kind of access, digital imaging, and obviously we hold their genome. And we make that available through what we call a research environment, which is AWS hosted. But that is in a pseudo-anonymized fashion, so we give them an identifier and no one knows in theory who they are. So we have a vast amount of data. We also link to what we call national registers. So in England, anyone that's registered with a cancer that local hospital site has to submit data about that individual to the National Cancer Register. So we're quite lucky, actually. We've we can kind of tap into that resource, so we can identify just from kind of histology about tumours, dates of operations, types of operations they've had. Actually, that kind of register provides a lot of data. But like you say, Bob, like that data set does not lead to research grade qualities, just to work out simple things like disease-free survivals or progression, we can't really do. So because of the way our consent works, we're allowed to go back to NHS clinicians and sites and actually retrieve from the medical records as well. So we're now doing that as well to add to our data resource. And I think the other thing that also is the complexity of large-scale data. I think for our researchers, they access something like 72 different data tables just to kind of work through that kind of participant kind of longitudinal data set. So actually we need to really push towards a common data model ourselves. But even that has kind of research limitations as well. So it's just working through not only what we think is right, but also what our end users need and how we're going to answer their questions for them, really.
And this is I'm just going to throw in this question because I feel like I don't like using the term double clicking on something. It's so technical. But let's zoom in a little bit on that. When we think about what our users need, how are we hearing what our research community needs? I open this up to all three of you. How do we know?
So for Genomics England, when we started the program, we realized that actually we need to work as a collaborative organization. We couldn't do it all ourselves, so we reached out to kind of what we felt were key opinion leaders in specific diseases, and we worked with them and ultimately their academic groups. So actually we have a network of nearly 3,500 academic researchers that are predominantly UK-based, but basically around the world. And they are broken down by disease type, so we call them GSIP, so Genomics England kind of research groups. And within that GSIP, we will kind of formulate, this is a colorectal GSIP, so they become the definitions of who do we go to, who do we ask questions about, what kind of panels do we do, what should we be improving our data sets with, what are the kind of research questions you want to ask, and how do we do that for you? So that kind of backwards and forwards between us and researchers has been kind of developed over the last few years, and has had its challenges, don't get me wrong. I think we all as researchers can be difficult to deal with. But I think fundamentally we want the best from the data that we're accessing, really, and I think that's been a good challenge for us to deal with.
Yeah, we did something similar with our TCGA, the Cancer Genome Atlas project. So each of our initial papers from TCGA were focused around an individual cancer, and each of those papers had a working group around that paper. And so the things that they needed for their paper are the things that we've incorporated into the CRDC and our data commons, as well as our cloud resources. And we're also just kind of in constant communication with the folks who use the CRDC through workshops and getting feedback, and even working one-on-one with folks to help solve their problems.
So my thinking about this has changed over time. I completely agree with what we just heard. I think that's 90% of what's going on. I think something else has happened also. And, we built our first commons from 2014 to 2016. That's when TCGA was a petabyte of data. And so when you had a petabyte of data, that meant the people who could analyze a petabyte of data in a secure, compliant fashion was very, very small. It was limited to some of the largest research labs and some of the pharma companies. And, progress was made, but I think, from CRDC, the platform Tanya is talking about, and Genome England, there's been an ability to what we call democratize the access to data, so that others can look at it. And I think this is important is because, I was a bit of I came in this from computer science, and I would go to a conference and they would explain why, all we need is this much data and this much analysis, and cancer was just going to sort of fall apart in front of us. And, it's turned out to be much more complicated. Every time we get more data, the structure, the molecular subtypes, the complexity with microbiome, the complexity with the tumor microenvironment becomes harder and harder. So So, I think of this as from a more portfolio viewpoint, and I think one of the advantages of the platforms and commons we've built is you can really bet on a very, very wide range of the research community, and you don't know where the next good idea is going to come from, and just betting on the big labs or just betting on the pharma, I think what we can do with the platforms that have been developed is you can bet on everyone and just see what good ideas come out. And so I think of a portfolio of where these advances are going to make and how you serve the communities being very subtle. So the more we can enable individual communities to build what they want and do that flexibly, the more we can attack these very, very difficult, complex diseases like cancer. So I think we're in a time of transformation in how we think of how we get the community the tools they need to make the discoveries that the patients require.
Yeah, it's almost ask the community. It's a self-service situation, but also, you're right, we're hearing many, many more voices in this research space because we've been able to scale people's accessibility of data. Right? Democratizing data access is my whole team's charter, as you all know, so rings very, very close to home for me. And part of that is not only being able to scale the availability of resources to your researchers, but scale that access. And scalability means a lot of things, though, when we start to talk about big data, right? I mean, sometimes scalability, it's triggering for us as data custodians, as it were. So I'm going to ask Tanya, when you think scalability, what do you think of?
So as I mentioned, we have about 4 petabytes of data. We started off with 1 petabyte of data. We copied it twice, once to Amazon and once to Google back in 2014. That 1 petabyte of data took about 4 months, I think, to get the whole data set uploaded onto so you can imagine how much 4 petabytes would take, right? So to me, scalability, we're 4 petabytes and growing exponentially, right? So I could easily see us hitting 8 petabytes in the next year or two, and from there just up and up and up. And one of the things that we're concerned about, of course, is the cost of storing all this data. We need to store the data to make it accessible for our community, but the cost for storage is going to be a ever increasing part of our budget. So we need to look at the data, and we need to evaluate what we do with the data. Do we need to keep all of the data on the highest availability disk, the most expensive disk? Are there data sets that are not being used very often? Do we maybe put those data sets on cold storage and pay less? We're looking into compression algorithms to make the data sets smaller, but we still want to make them accessible to the users. So if we compress the data, we still have to make sure that compressed data will work for our users in the cloud. So and also the other thing, again, we've got 2 copies of the data. Long term, do we need 2 copies? Can we keep the data in one place and still make all the platforms able to interact with that data? So that'll be a very important next step, I think.
Yeah, definitely duplicating data is something that we all want to avoid simply because you're literally doubling your data footprint. But also, does that really speak to the tenets of what open data is, right? Which is de-siloing data and deduplicating it and maintaining a single source of truth for your data set. But that does bring into question, interoperability. There are so many different things we can also think of. Scalability is triggering. Interoperability can maybe be triggering for some people in the audience as well. What do you think, Bob, when we talk about data interoperability, what are our biggest challenges right now?
Well, before we get to the challenges, I do want to call out in cancer just the advances we've made in basic interoperability over the last 5 years. With GA4GH and some of the standards they've developed, if I have a BAM file and it's in a cloud, I can pull that into a tool fairly easily. I can have multiple copies of that. I can have on-prem and in-cloud copies. I could do that not only for BAM files, but for any data object. So I could package data, I could have packages of images, I could have packages of bulk clinical data. So some things are quite easy. So when I have data objects, whether they be bulk clinical data or BAM files or images, I have pretty good interoperability. The challenges we have are the tough challenges when you have one cloud platform operated by one entity, subject to one regulatory and compliance and ethical environment, and we have to interoperate that with others to get data for many of these problems in which, cancer is still about rare mutations. And, I think more generally, biological discovery is about lots of very weak effects that interoperate. And, when I grew up, I did not say I want to study lots of weak effects that interoperate because that's too hard. But in biology, that's what we have. And so to study that, we have to interoperate. And so I think, what we need is to, sort of evolve not just the technical standards, but the policies that allow interoperability. And that could be quite general. I mean, we can have federated interoperability and ship containerized workflows. I'm the I'm the CRIO for our research enterprise, and I understand that we want to share, but the best way of sharing data is often to bring someone else's approved computation inside our security and compliance environment and return the results out, and that can be done in a cloud. With best interoperability. So I think we're going to broaden what we mean by interoperability also.
Yeah. How about you, Prabhu? What do you think as far as?
So probably going back to scalability first.
Yeah.
I think we've got a kind of slightly blinkered view because we've got a consent that allows us to acquire anything, but it can't go out. And so that kind of trusted research environment is kind of center to everything that we do. But that also, like Bob says, is kind of siloing our data. Like we have really rare pediatric tumors that we really should be engaging with those around the world, because actually that's the only way collaboratively we're going to learn from these. But we can't at the moment, and we're kind of stuck in our mindset. Well, it's not stuck in our mindset, but we have this kind of gold mine. How do we make that kind of interoperability then kind of comes in? So can we federate? What can we do? If everyone is on the same AWS cloud, is there a way to work through that? So those are kind of things we're thinking. I think the other thing for us is we started very much with the mindset we just need whole genomes, and we're now pushing that boundary with imaging. But there's also other data sets that we need to kind of think about long term. So RNA-seq, like kind of panel data, those are the things that also to scale the volume and the numbers. So potentially in the next, I think 3 years, we should have 500,000 participants. And then with that, you've got the whole genomes. Cancer, you have 2 genomes per participant, all of their imaging. It's suddenly like the scalability, the volume of data, how you're going to compute through that and analyze that becomes a kind of seismically, the numbers has become almost unimaginable. And I think that's where we're now really thinking and focusing. How do we do that? How do we prepare ourselves for that?
Mm-hmm. And that's the interesting thing, and I say this as a biologist, we hate to throw things away. we do, right? We hate throwing away data. It seems wrong to us at our cores. But there's such thing as not necessarily throwing it away, but potentially saving some money by storing it in colder disk. And to do that, to allocate data that needs to, let's say that we're like, we're retiring you, we're putting you in archive, you need to understand the patterns of data usage. And I mean, these large-scale data sets are so unprecedented in their scale that we're starting to pull out these really interesting patterns of usage. And I'm wondering, could you speak to any cool insights or patterns that we have multiple big data sets on the stage today?
Well, I'll say that the TCGA data set, our genomics data from that has been hands down our most popular data. That's I think in the GDC you have 2 petabytes downloaded every month of just the TCGA genomics data. It's really quite impressive.
I mean, TCGA basically set a precedent for everyone around the world. Like, you know, you can go to basically any algorithm anywhere on imaging, and it's probably quoted from TCGA. That's become the gold standard, and it's like what everyone follows. So, yeah, it's credit to you guys for setting that up, really.
Yeah, I want to twist it around because I think there, you know, as Tanya said, over 2 petabytes of data are accessed each month from the GDC, which is, you know, most of that is TCGA. You know, I think there's a rule here that's easy to forget. By the time you ask how much of the data is accessed, you're so far down, you don't have many knobs to turn. I think the reason the TCGA, I mean, first of all, there are a couple of reasons the TCGA is accessed so much. One, there was an awful lot of care and energy put into the creation of the data set. And two, there was a huge amount of care and concern put into the curation of the data set and keeping the curation up to date. And you know, these days with the commoditization of sensors, it's very easy to produce data. It's very hard to produce good data that's worth analyzing and worth analyzing year after year. So, you know, the question that most of you should ask yourselves is, this data that was just dumped on me from sensors, is this data that is valuable? Or, and if it is, then am I willing to invest in the time and energy to curate it and to keep it curated and to harmonize it, that is, analyze it with a common set of pipelines so that it remains valuable to the community. So by the time you ask, you know, by the time you're at the end, you know, it's hard to go back and create good data sets. It's hard to curate and it's hard to keep it curated. So, you know, the life cycle of data and the economics of the sharing, you know, most of the cost is even though the cost of creating some of the data, most of the cost is in the curation over the long period. So I think we need a better understanding of the economics of data sharing and its impact on research, because these questions are quite hard.
Oh, I didn't mean to ask hard questions, but here I am, right after lunch too. But I guess, you know, when we think about curation and annotation and basically making sure the data are easy to use, I think inevitably we all drift towards this space in big data where we go, well, machine learning. Right? Every single one of us says, I'd like to apply AI/ML to my big data set. It's okay, I know you're out there too. We've all thought that. So and actually we have quite a few talks coming on after this that talk specifically about the application of AI/ML in clinical decision making, medical imaging, et cetera. So, you know, when we start to think of this as the next frontier, what are we going to have to do as a community?
Well, I'll just remind someone, so how many of you have looked at the first 2 or 3 principal components of histopathology images in cancer? Okay, if you look at the first 1 or 2 or 3 principal components of, say, in the GDC, one of the most accessed data sets is the 10,000 or so slides from TCGA, histopathology H&E slides. You can easily figure out what hospital provided the slides by just looking at the principal components. And, you know, most healthcare systems, especially, you know, from academic medical centers that contribute to them, have quite different patient populations. And so because you see, it doesn't mean you can't get around this, it just means that, there's a lot of interesting work to be done before machine learning completely solves all our data curation problems. Now, it's going to help a lot, and I want machine learning as one of my friends, but it's when you have a powerful tool, it's much easier to, shoot your foot than to do something good with a powerful tool. So machine learning is a wonderful tool, and when it's used by good people, it can't be beat. But giving machine learning to people who don't understand the data, who don't understand the software, and then ask them to curate the data, and then be surprised when they do this with some biases there, you can't be surprised. So I'm very optimistic about machine learning, but I think there's full-time employment for quite a while for the machine learning people doing data curation.
Talking a very good job market right now.
But also, I think we've all, as a group of people, have all said machine learning is going to solve all of our problems, and it's going to be amazing, and we're just going to retire very early. But we might get there. But actually, at the moment, I think even for what we're doing, is very specific questions like, can we actually answer what has happened here? And it's only one use case, and can we use ML in that? Now, the issue there is obviously, can that model be scaled to look at other questions, and can we manipulate that model? I think at the moment what we're looking at is what are the questions machine learning can help us address, and is it then a clinical decision support, and can it go to clinical practice? So those are the steps I think we've just got to go through before we suddenly jump and say, hurrah, it solved all our problems. It might do, and I think that having that kind of question about it and actually really testing the value of it and really kind of knowing that it is there as a support for us rather than doing all of our work, I think that's the right thing. But there is obviously a value to it, and I think people are seeing that, but in very limited cases, and I think that's where we've got to look at how to scale that.
Yeah, we're also doing very kind of specific things with machine learning. So one of the things we're doing is the pathology slides, for example, that Bob mentioned, sometimes can have patient information on them. Birthday, name, address. So one of the things that we have to do is de-identify these images. We have to make sure that there's no patient information on these images. And the way that's traditionally kind of been done is someone looks at it, right? Is there a name there? You black it out. We're using machine learning to try and do this in an automated fashion. And you'll probably hear more about it at the next session, but that's one of the things we're doing that'll allow us to go through 10,000 slides much more quickly than by having someone physically look at each slide. One issue we did find with it, though, when we created some fake data for the algorithm to find, it didn't identify an address as potentially identifiable information. And the reason was because it wasn't a real address. So it was actually too smart. It looked up the address. It said, that's not a place, so it can't be an address. So maybe we have to be a little smarter in what we feed the algorithm as well.
Yeah, well, and that also brings up the value of synthetic data. And what kind of, the beauty of synthetic data is that it doesn't necessarily need to be as controlled access as the data sets that we're talking about today. But there are some real drawbacks. One of them is that we may not be actually talking about a real address or a real person or a real genomic sequence. But is there a place for synthetic data in this world, or should we be working with real world evidence?
I'm a big fan of synthetic data, but I think it's going to take a while. When, these days, when I started my career, people were working quite hard on voice recognition and automatic translation, and it was very difficult to predict when that was going to be ready for prime time. But now, every day we ask, our devices questions and we get answers back. And, a lot of times I can't tell the difference between the response and a real person's response. They sound so close to each other. So, clearly synthetic generation of data is absolutely critical. We know about deep fakes and so on. I think for for certain data, it's going to be sooner. It will be there for all data eventually. I think the challenge right now with clinical data is we just have a long ways to go to get large, harmonized, curated stores of clinical data to do the training. So it's really clear it's going to have an impact. It's not at all clear for a particular type of data, for a particular problem, when that impact will be. But I guess we could ask one of the AI systems to tell us that.
Does somebody have Siri on their phone? We could ask. How about you, Prabhu or Tanya?
So we are creating synthetic VCFs. So we are looking at doing BAM files, but VCFs at the moment we've done, and like Bob says, there is a value to that. Synthetic clinical data, again, like, I think the problem is like fundamentally, like as a pathologist, I can say this, we're all different. We write like crap down sometimes on a pathology report, and it's just like what we want. It's just our own kind of handwritten report. And everyone is then different, like how I kind of write ER status, like another person in another room will do it very differently. So that variation in kind of what you're taking in, the quality of the data coming in, and actually then what you can create as kind of synthetic models and actually common data models is really skewed. So I think we understand kind of that genomic synthetic element. Like Bob says, we're looking at kind of images, we're looking at the clinical data sets, and fundamentally there is going to be a value, but I think we're still exploring that, I think.
Awesome. Well, we have a few minutes. I'm a little bit ahead of schedule, and so I'm sure that we have some burning questions from the audience for our panelists. They can't run away right now, so feel free to ask them lots of uncomfortable questions, and we do have a mic runner. Maybe nothing uncomfortable.
We have a question here.
I think
there's one too. You have better eyes.
I'm certainly not an expert in all this stuff, but I'm just ask two questions from a common standpoint, more for Dr. Davison. One is dealing with environmental contributing factors in a data set. Like, for instance, 6 Philadelphia pitchers died of cancer, maybe potentially from the radar or whatever, in the past 20 years. And that type of thing maybe affected others, or I don't know if you isolated that cancer, that data set, or is that something that you look at in dealing with that? And just one on the follow-up question, intergenerational cancer. My doctor, my dad had cancer, he died from lung cancer. My sister had cancer of the elbow, and it went up to her lungs, and she died. And hope, God willing, the rest of us in the family are okay. But many generations, it either skips or goes to the next generation or whatever. And it sounds like you're evaluating all these amazing things, but you're not like factoring in data sets that involve either intergenerational or environmental and things that affect our day-to-day lives as people.
Yeah, that's a really interesting question. So as Bob has talked about a little bit, and Prabhu as well, the data has to be annotated really well. So environmental factors are something that would come into the annotation. One that kind of comes to mind is was the person a smoker, and how did that affect their cancer? So some of those environmental factors we do have some annotations for, but it's not enough. I completely agree. And some of the cancers that we do study, there are some intergenerational studies done, but not enough. I agree. That we just don't have enough of either of those.
I think we had another question up closer, maybe.
Thank you for the great talk and the great discussion around precision oncology. Bobby mentioned a little bit earlier that we're starting to generate data silos now in the cloud, each having their own operational boundaries. what would it take to start to bring all of these great data commons, great data sets together? What is that next step that needs to happen for these communities to start to come together?
I think that's a great question. I would say there's three dimensions. There's the dimension of what the technical standards are, which we've talked about for the APIs. There's the dimension of the second dimension after the APIs and standards is, what is the interoperability policies that, respect the patient consents, but, are designed to accelerate research because it's everyone's right to benefit from medical research. And then the third, I think, is, to me, one of the more exciting ones is, to broaden the playing field so that we just, if these days, the first thing people says, well, you've built that, I want your data, give me your data and go away. I think the third dimension is a more nuanced discussion of how do we interoperate where both platforms benefit from each other's data and both platforms have good policies and other things in place so that they're confident they can interoperate. But just as importantly, as I briefly mentioned, how can we get more creative? And machine learning can do a lot. Summary of data can do a lot. A lot of the advances in our understanding of the structure of data can do a lot. How can we be more creative? Like if the large platforms with cancer data want to interoperate with Genome England, that doesn't mean we move the data to one or the other. It just means we get better and better at understanding how we ship computations and how we iteratively compute on both sides, but letting the data in there. So to me, that third dimension in which we broaden what we mean by interoperating to have computation that's much more flexible when partial results, some masking of data, et cetera, so that we have a lot more flexibility in how we deal with those first two dimensions.
Thank you very much for your information. This has been, for at least us, one of the best topics of the day, by far.
Can you say that again? I couldn't hear.
I think this is being recorded. That's excellent.
We're very much in the clinical data curation space, and like you, we're always challenged with, trying to get it as clean and as accurate as possible. What steps have you guys taken to get to that? Or not?
So the problem we have is actually we have multiple sources of data. So we have registration data, we have kind of some longitudinal data that's come from NHS sites, we then have national scale data sets that have come in. So even for one individual, we are then picking up multiple kind of dates of operations, multiple events that are occurring. We're quite lucky that the national data sets, and one of them has become gold standard because they have manual curation, so they've already done that kind of curation phase. But then we're also facing the challenge that even kind of the building of our common data model, there are other fields that we're kind of finding disparate sources of data that are kind of, in terms of QC, we're really kind of struggling on that. And at the moment, it's manual review that we're having to do, which doesn't really answer the question, but actually is giving us a benchmark that we think that we can build on and scale out to. So then, kind of, as we've done that for, say, a couple of thousand patients, how do we then build on that again? So, the term of NLP and like natural building and kind of where we go from there. So at the moment, for us to deliver what we believe is a gold standard is still manual review, and we haven't got around that yet. But it's a question that we're trying to challenge ourselves internally to get to that, really. So like in England, I think we've got 350 registrars, like people that will do this for all of our cancers in England at the moment, and they take, I think somewhere in the region of 18 months to do that for everyone that comes in. So that's what we define as being the best way to do it. But actually, I think we're really open to the idea of how to do that better, really.
Yeah, I think it's a huge problem. One of the things that we do is each of our data repositories is kind of a gate, right? And so in order to get the data into the data repositories, we're basically asking for certain metadata around the data that needs to be formatted in a certain way. And there's certain things that you can do. You can have a little script that double checks, you know, that the gender, for example, is one of 3 choices, or we call them common data elements, and that the repositories across the entire CRDC are using the same common data elements. Again, because then we can query across all the data sets uniformly. But it's hard, and some of the data sets, like for example, proteomics has very specific pieces of information that just aren't represented in some of the other repositories. So there's some additional fields that won't be across all of the data sets, but it's a tricky problem.
And I think you asked a key question, and we heard, you know, when it's taken seriously, how it's done. You know, it's done quite seriously there, and it's manual. CRDC and GDC take it very seriously. I think the challenge is not everyone understands when they build a platform the importance of curation, and so I think it's. And this is why, you know, I call out to this group. You have to if you're the decision maker, you have to understand the importance of curation. You don't get a lot of credit for it, but in the end, it's one of the main factors for the use of a platform and of data. And if you're, you know, it's sort of everyone's responsibility, because it's not the most recent, the most flashy technology, but it's so important. So there's an education component required by all of us to explain, if you have, I'm just going to make up a number, $1 million to spend, what the right number is for curation versus the community versus the compute. Those decisions you make when you're setting up the operating budget of a platform are absolutely critical, and people, when they don't spend enough in curation, are surprised that people can't use their data. So I think there's a huge educational component to this. And then, if you think about the economics of curation, you have a tough decision you can make, is how much it's done centrally by the platform and how much you push to the researcher. If you push too much to the researcher, not enough gets done. If you do all curation for every researcher in the platform, there's no money left to operate the platform. So, when I was little, I used to think all you need is a clever algorithm. Now, I think you not only need a clever algorithm, you need a deep understanding of the economics of data and its impact if you're going to make good decisions about how to build these research platforms.
Hi, my name is Benita Bottom with Ventec, but I'm involved in the canine world. And I have a question for you, Dr. Davidson. Are you involved in the University of Missouri Cancer Research Partnership that National Cancer Institute is also involved in? I mean, there's obviously a lot of innovations. We do a lot of research with our dogs because we love them. And lots of initiatives.
I'm not sure if that data set is in our integrated canine data commons, but maybe we could chat afterwards and connect. Yeah, I'd love to talk to you about it.
Fun fact, I also worked in a dog genomics company for a few years, so I think I know the project you're talking about.
And you're a DVM. So question for Dr. Davidson and Dr. Grossman. So I heard you talk about having like 6 data commons for your different cancer data sets. How do you know when to direct data to go into one of the 6 or to create a 7th? And then a question for Bob. You have a lot of data commons in other domains and disciplines. Is there like a sweet spot for this is when we create a new data repository to data resource versus try to integrate into an existing one?
Yeah, that's a good question. So One of the repositories I mentioned is our Cancer Data Service, which is the one that'll take the data sets not otherwise appropriate for the other 5. We do have kind of pilots out for 2 additional kinds of data commons, so immuno-oncology data and population science data are 2 things that we've heard kind of across NCI that we need. And so the way that we kind of decide that we need a new repository is again, just working with our colleagues at NCI, the folks who are either generating data or the folks who are funding those who are generating data. What kind of data are they generating? Which ones don't have anywhere to go? So in January of next year, we have a new data sharing policy coming out, and everyone who has a grant from NCI really needs to be sharing their data. And so the program officers are coming to us saying, there's nowhere for my grantees to put my data. What do we do? So that's kind of how we do it. We gather the feedback across NCI and then start maybe a small pilot project to kind of gather some data and make some inroads to it. And then, so in the next couple of years, you might see 8 data commons instead of 6.
And briefly, I think you asked a good question, and I don't think there's a simple answer. When I started up building these, I thought people were interested in my opinion. Turns out no one's interested in my opinion. If someone has data and funding, we think of them as the sponsor, they have an opinion. In general, they want their own platform because they see their platform as different than others. I think that was certainly the case when the platforms were large and expensive to build. I think we're going to see, the ability to bring out almost a commons as a service in Amazon and other cloud platforms. That's going to lower the cost to build a cloud. Now that's to build a commons. That's good and bad. It's good in that more research communities can build it fit for their own purpose. It's bad in the sense that we don't want further and further siloing. So I think that's the question you ask, when do you add your data to a platform and when do you build a new one? I think we could, I would like to see it in 3 or 4 years phrased slightly differently, as it's fairly easy with standards-based infrastructure to add a given data set as a data object to one or more clouds. So let's just do that. Let's take no pride in ownership of that. That's fairly easy to interoperate. Then all the interest comes, in a layered stack of how do I build services for research purposes that satisfy a given community, interoperate as required. And I think I hope that, we can do this technically now. Most people don't think like this. I would like to see the commoditization of the lower levels of these platforms just be, something that we take for granted. We can. You don't want to go to the lowest cost. You want to have interoperability. You want to be able to pull the data out, but you take that for granted. Then the interest is, what is the right way to use standard services or build your own, and how do they interoperate so that you're acting at a higher level? I mean, these days, no one thinks about who owns the bits, when you're building applications. But in this space of biomedical research, we still because of the consents and compliance and security, we put a lot of emphasis on that, and I see that changing over time. Good question.
So we have, the next session, I believe, starts at 3. So I cannot say that we will be here for a very long time to take additional questions off the stage, but potentially we might loiter a bit outside if there are additional questions. I think we need to jump. Can we jump very quickly to the next slide? I'm under contract to ask you to please consider our cloud training, digital skilling workshops. Please do visit our skill builder and our certifications. And please do take the session survey. I very much enjoyed hearing your questions. I have enjoyed my time here with you. Thank you for joining us today, and we'll see you outside.